Deborah, and I'm a physicist. And today, we're going to talk about vectors. Last week, we talked about things that moved in just one dimension. So, from left to right, from right to left, up, or down. But not more than one of those at once. But in the real world, most things move in more than one dimension. They might go around a corner, or they might go on diagonal. And we need to be able to describe that kind of motion. When we want to know about things that are moving in more than one direction, we have to involve something called vectors. These are some vectors. Now, what is a vector? Actually, it's anything that has both a magnitude and a direction. So a lot of our examples are going to be focused on things moving in more than one direction, so to the left and right or up and down at the same time. But actually, there's nothing that says that vectors have to do with motion. Quite a lot of quantities in physics are vectors. So forces are vectors, electric field is a vector, magnetic field is a vector, lots of things are vectors. But although it's easy to say what a magnitude and direction is, I find it's actually kind of tricky to get some intuition. So let's start graphically and then move into math. And then whichever one works for you, keep that one in your brain and don't worry about the other. All right, this is a vector. As you can see, it has some magnitude, some length of the vector, and some direction. It's pointing off sort of to the upper right corner of the screen. We don't really know what the magnitude is in terms of numbers. We don't know what these directions are. I haven't given you a coordinate system, but we know that there's some kind of magnitude, some size of the vector, and some direction where the vector is pointing. Now imagine we have a second vector. Well, this vector is the exact same. It has the same direction, it's also pointing off into the distance, and the same magnitude. Okay, now suppose I have another vector. This one's pointing in the same direction, but it has a different magnitude. The arrow is now half the length, and so it has a much smaller magnitude, even though they're pointing in the same direction. Now, depending on exactly how we defined this, to be the exact same direction, they might need to be on top of each other, but that would be hard to see, so I've separated them out. On the other hand, we can also have a vector that is in a different direction, but with the same magnitude. This arrow is exactly as long as the other arrow, but now it points in a different direction. So what is not a vector? Well, anything that just has a magnitude is not a vector. It's what's called a scalar. The most common example of this we run into in physics, or one of the most common examples, is speed. So the vector is velocity, how fast are you going and in what direction? And the scalar version is speed, which only tells you how fast you're going, but not in what direction. There are other quantities as well that are just scalars, anything that just has a magnitude. Technically, any regular number is a scalar. So if I tell you that I doubled something, then technically I multiplied that something by the scalar 2. Now it turns out there's actually 3 or so ways to write a vector, specifically in Cartesian coordinates, which means like x and y coordinates. There are other coordinate systems, but the ways to write a vector actually stay the same. Some of the details just change. Okay, so first, how do I denote that something is a vector? So there's 3 basic ways I can do it. If my vector is called x, I can have an x with a little arrow over the top. I can have an x with kind of a quasi-arrow over the top. Or I can have an x that's bolded. Now usually you'll see the x that's bolded only in print, and you'll generally see the x with the half arrow only in handwritten materials. I'm actually going to stick with the x with the full arrow for the rest of the video because I think the bolded is hard to read in the Microsoft equation editor. The first way you can write a vector is to write it down like this. So you say your vector x has components a in the I hat direction plus b in the j hat direction plus c in the k hat direction. Now this is kind of a fake out because you're not actually adding together a plus b plus c, you're just saying that the 3 components are a in the I hat, b in the j hat, and c in the k hat. Now what in the world are the I hat, the j hat, and the k hat? Now for reasons I do not know, the I hat means the x direction, the j hat means the y direction, and the k hat means, if you have it, the z or z direction. This is my most used vector format, but I have no idea why it's I, j, and k. My high school math teacher would say it's because of the old men in Switzerland. The second way you can write a vector is just a little bit more straightforward version of the same thing. So your vector is x, it has component a in the x direction, b in the y direction, and c in the z or z direction. And this is, again, straightforward. You can easily follow x, y, and z and know where your vector is pointing. But sometimes you want to take up a little bit less space. And that's when we have this kind of format where you say your vector x is usually angle brackets, but can also be regular brackets. I find regular brackets confusing. So here we have angle brackets, A, B, and C. And all three of those ways of writing a vector mean the exact same thing. We know that our vectors have both magnitudes and directions, but sometimes it's useful to just know how big the vector is, to just know its magnitude. So we want to be able to calculate that. So first, just to formally state it, if I have a vector x, which has components in the x, y, and z directions, a, b, and c, then the magnitude of that vector x would be the square root of a squared plus b squared plus c squared. But it's a little unclear where that comes from. And so to explain where that comes from, and for the remainder of the video, I'm actually going to switch to 2 dimensions, so the math is just a little bit easier, and we can talk about how we get that this is the magnitude. Let's imagine we have a 2-dimensional vector r, with components x naught in the I hat direction and y naught in the j hat direction. Now I've drawn x naught here in purple, y naught in orange, and the total vector r in green. You'll notice this makes a right triangle. And this allows us to use the Pythagorean theorem if we want to find out how big that green line r is. Now that green line is our total vector, so its length is the magnitude of the vector. So we know from the Pythagorean theorem that the square root of the sum of the squares of the two shorter sides is the length of the hypotenuse. In other words, the magnitude of r, which we can write either with these double bars or just by removing the vector symbol from on top of the vector's name, is the square root of x naught squared plus y naught squared. That's the same equation we had before, but now that we can see it as a triangle, we can better motivate why that equation works. Now suppose we just wanted to know the direction of the vector. We no longer cared about the magnitude, how big it was, we just wanted to know where it was pointing. Could we do that as well? Of course we can. Imagine I have my same vector, r, which is composed of 2 components, x naught in the I hat direction, y naught in the j hat direction. We already said its magnitude is the square root of x naught squared plus y naught squared. But now I want to know this angle theta. What direction is this vector pointing? How could I find that out? I can find it out with the magic of trigonometry. You may recall from previous math courses that the sine of an angle theta is the opposite side of a right triangle divided by the hypotenuse of a right triangle. Cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. Now in our triangle here, the purple line is the adjacent side because it is adjacent to our angle theta. It touches our angle theta. The orange side is the opposite because it does not touch the angle theta. It's on the other side of the triangle. And as we already said, the green side is our hypotenuse. Now, if I only know that the vector is x naught I hat plus y naught j hat, I could find out the hypotenuse, and then I could use any of these trigonometric functions. But it might be easier if I stuck with the one that uses the components I already know. In other words, tangent. Now to find the angle theta, I take the arctangent of the opposite, y0, divided by the adjacent, x0. So I have that theta is equal to tangent to the -1, or the arctangent of y naught over x naught. And that value will give me the angle theta. I will not be able to calculate this by hand, most likely. I will want to grab out a calculator. One thing to note is there are 2 types of units we can use for angles, both degrees and radians. The difference isn't super important here, but it's very important that you know which units your calculator is using, or else you'll get incorrect answers. Let's suppose I wanted to do more or less the opposite thing. I wanted to break my vector into its x and y components when I know at the starting point the vector's magnitude and the vector's direction. Well, I can do that too. So imagine I have a vector in the xy plane with a magnitude r that's pointing at an angle of theta degrees. This is essentially the final results from our previous 2 sections. So I know my magnitude now, I know my direction, but I don't know how much I have in the x and how much I have in the y. How do I find those components? Well, I return to the magic of trigonometry. So now we're going to use our other 2 trigonometric functions, sine of theta and cosine of theta, because we know our hypotenuse r, but we don't know our opposite y0 or our adjacent x0. So now let's plug in what we know and we don't know. And we know that the sine of theta has to be equal to the opposite, y naught, divided by the hypotenuse, r. And the cosine of theta has to be equal to the adjacent, x naught, divided by the hypotenuse, r. Now we do a little algebra. And we find that y0 has to be equal to r times the sine of theta, and x0 has to be equal to r times the cosine of theta. Very quickly, let's talk about how to do a little bit of vector math. First, let's imagine I have two vectors, we'll call them a and b, which have those values, and I want to add them together. Well, this is easy. I just add together their components. My new vector c is the sum by components. So my new vector c's I hat component is p plus s, and my new vector c's j hat component is q plus t. Easy peasy. Now imagine I have two vectors and I want to subtract them. Let's keep the same vectors. Well, my new vector c, which is the difference between a and b, is just the difference between the components in each direction. So my new vector c is p minus s in the I hat direction and q minus t in the j hat direction. Now let's suppose I want to multiply together two vectors. We're not going to do that right now. It's complicated. There's a couple different ways you can do it, but neither is entirely straightforward, and we'll save those for later. But suppose I want to multiply a vector not by another vector, but by some kind of scalar, just a number. We'll call it d. This is also easy. We have that the vector c is just the scalar d times the components of the vector a. So we'd have d times p in the I hat direction plus d times q in the j hat direction. Here's a quick summary of everything we talked about today. Remember, vectors have both magnitude and direction, while scalars just have magnitude. If you need a quick reference for calculating magnitudes and directions or components, you could take a screenshot. And remember that when we do math with vectors, we can add, subtract, and multiply by a scalar just using components. But vectors multiplied by other vectors are more complicated, and we should be careful. I know from past experience that vectors can be kind of challenging when you're starting to learn physics, but I hope that I've shown you today that they're not really all that scary.